Hello, in this video we are applying the complex number algebra that we talked about last time to the Ford-Euler case and seeing whether the Ford-Euler, which was conditionally stable for exponential decay, is still stable when you go to oscillation. Okay, I'll hand over now to the board.
Okay, so we're now in a position, having discussed in the last video, so all the background features of this equation dx by dt is I omega x. Remember, this is oscillation case. And we now know that x is complex, and really what we're thinking of is the real part of both sides when we write this down. And the solution is a superposition of cosine and sine solutions, and the omega corresponds to some degree to our frequency, or how fast our wave is oscillating. So we've done all that background, and we can now do the stability analysis. And we want to do a stability analysis. And actually things become quite easy for the Ford-Euler case, because what we do is we recall the Ford-Euler result for the amplification factor. And there we remember we had A is 1 minus lambda delta t. Okay, and A was real. And now we remember actually our problem is simply we are changing minus lambda, and we're changing it simply to I omega. So we're now, and if we just do that, then we can just, we don't have to, we could do the algebra again, it's just a few lines, or even 2 lines, but we can actually just substitute, we can just substitute minus lambda for I omega. So now, our A, so that A was real before, yeah? That's before. Now A is complex. It's 1 plus I omega delta t, and it's complex. Okay, so we've just quickly gone to our result for the oscillation case just by observing that the structure of the equation is just transforming minus lambda to I omega. So this is why we don't bother with putting reals on both sides, because algebraically it's very convenient. But that, I also wanted to just make you aware of the background, so you're sort of fully informed about what it is you're really doing and what sort of situation you're handling. Okay, so let's just write that down again. So A is 1 plus I omega delta t. Now for the oscillation case, for Ford-Euler method. So for stability analysis now, involves considering the complex modulus of A. That's what we're going to do algebraically in a minute. But let me just give you a bit of background to why we do that. Remember, stability analysis is about comparing numerical and true solutions. So in the case of exponential decay, if it fell off, the numerical solution fell off, even if it didn't follow exactly, then we'd still say it's stable. With the oscillation case, we have to think a little bit differently. So now the true solution, and I'm just going to drop the reals, is x star equals x naught ECI omega t. And we know that x star, the complex modulus now, we derived this last time, is x naught is constant. And what this corresponds to sort of intuitively is that we have oscillatory wave set by the initial conditions. In this case it's a sine wave. So this is the real part of x star. But we know that this solution has an amplitude, yeah, of your oscillation, sometimes referred to like that. So the fact that the fact that the complex modulus is constant corresponds to the amplitude of the sinusoidal solution. Yeah. So if what this means that when we say the true solution has the complex modulus is constant, it means that the true solution, that the sinusoid that's equivalent that I showed in the last video, has constant amplitude. So we can consider sort of different scenarios, and this will become right into sort of the practical on ODEs that we'll go through in week 4. Okay, so there'll be sort of practical applications here. So we have if we have the real part of our solution x, and this solid line is the true solution. Now if I just change color, I try not to do this too much and if people don't like it, but the numerical solution then is, if it's unstable, it's going to mean that it's actually going to grow out of bounds. I haven't drawn that very well at all. You see, I'm not employed on the basis of my artistic skills, hopefully a bit more on my mathematical skills. Here we go. You get the idea though. This is an example of unstable. So this would mean that the complex modulus increases with time. And this is a numerical solution, complex modulus. Let me change back to okay, so the numerical complex modulus increases with time. So this is what we're going to look at, is that, so this in our new nomenclature, we now have this thing A is now complex, and remember A is the ratio of one step to the other, so it's xn and plus 1 to xn, right? So it's this ratio that takes us each step beyond it. So we're going to now infer that for oscillation, and this is why it's important to do this background work that I did, because it starts to make a bit more sense. If A is 1, then we call it stable. And that means if A is 1, it means a numerical solution maintains its amplitude. Yeah, so the solution just goes along like this, keeping a constant amplitude with time. Okay, but conversely, so don't forget, those two things are complex modulus, not absolute value. Conversely, if A complex modulus is greater than 1, we have a true solution that grows. So that means the amplitude of the solution will grow in time. Something like that. So algebraically, it's probably simpler than in understanding exactly what you're looking at, what the underlying problem is. But I'm trying to give you both viewpoints because I think understanding of what you do is so important. So important for enjoyment of what we're doing. You know, just going through algebraic steps is dull, but when you know the reasons behind the algebra. So we're going to just go through a few examples. We're going to calculate the complex modulus, and we're going to look at when they are greater than 1 and when they're 1. Now, observers of this stuff may have noticed that I've neglected the other aspect of a wave, which is its phase. I've deliberately done that. I felt that looking at the phase aspect of this problem is beyond the scope of this module, but you can also analyse the phase error introduced in this complex number quite simply, actually, using your complex numbers if you want to take it further. So we're just going to currently think of the amplitude of the wave and think when modulus of A is greater than 1, then it's unstable. Modulus of A is less than 1, then it's stable. Okay. Okay. So let's return to our Ford-Euler result. To Ford-Euler oscillation. We have that the complex amplification factor is now 1 plus I omega delta t. And we now know all we have to do is find the complex modulus. Find complex modulus. And a lot of the time it's simplest just to do the modulus squared and then take the square root. Yeah. So again, remember the modulus squared is simply using Pythagoras. So I'm just going to pause a bit and then maybe you can think about what the answer is to this solution. So I'll give you a couple of seconds. Okay, so the answer to this is something we just use Pythagoras. We do 1 plus omega squared delta t. And just to re-emphasize, it's a plus here, right? Not a minus. You don't square the I. Okay. Important. If this is something that's lost in your sort of, either you did it or you didn't heed it at the initial time or forgot about it, do go back to complex numbers, basic complex numbers stuff, and remember what the modulus squared, or come to me if you require further help. Okay, there's no embarrassment for getting it wrong when you learn it, but it's a bit more embarrassing when you do it in an exam or in a coursework. Okay, so we now have and we're just going to take the square root now. That will give 1 plus omega squared delta t squared to the half. Okay. I'm just going to rewrite that at the top of the board. The complex modulus of A is 1 plus omega squared delta t squared. So remember, delta t is your time step, is greater than 0 by definition. Omega is greater than 0 by definition. And I'm going to ask you another little question and then come back. Is this method stable? I.e. the Ford-Euler, is it stable? So remember our criteria on A that we just wrote down previously? Just have a little think about that, and I'll come back to you. Okay, so the point is that modulus of A, because delta t is greater than 0 and omega is greater than 0, and we've got a 1 in here, is greater than 1 for all. Okay, let's just use a little bit of analysis notation for all delta t. So that means the oscillations grow in time. Yeah, because it's greater than 1, because you're multiplying a number greater than 1 each step. But the true solution keeps constant amplitude. So this is a great thing where the sort of practical should mesh with the theory, you know, in sort of the practical on ODEs. In fact, this is my favorite practical, I think, because it has a lot of information in there if you sort of are willing to go through all the steps. So you'll find we'll start off with a true solution like this, which is constant amplitude. But you'll find the forward Euler then, with its amplitude factor greater than 1, sorry, its amplification factor greater than 1, will grow unbounded. This is so what we have is a situation now where the stability depends on the context, and that's the bit you have to get used to with this topic, is that it's not a universal result. So if we go back to our forward Euler, we found two things, and then I think we're going to stop and resume. So for exponential decay, that was dx by dt equals minus lambda x. Forward Euler was conditionally stable. It's conditionally and by conditionally stable we meant it needed sufficiently small time step delta t. But for oscillation, dx by dt equals I omega x, where x now becomes a complex number, and we're taking real both sides really. For that case, for oscillation, it is, so it's called forward Euler Fe. Fe is unconditionally unstable. So it's always unstable. And that's the worst type of numerical method, the one that no matter how you change the numbers in it, it's not going to work. So that leaves us with a big question then, is how do we improve on forward Euler? We know that forward Euler is only first order accurate, so we can improve the accuracy, and is not always stable. Okay, and you can see we've already brought in these two ideas of accuracy and stability, which are core to numerical methods. I sometimes show a swing. This analogy shouldn't be taken too far, but it just wants me to emphasize that these are the two key concepts that flow through all this material. You've got the accuracy, the thing to do the Taylor series and the bit that you're lopping off, order delta t to the whatever, and the stability that we've analysed before, and you have to consider both together. So that's really where the rest of this part of the module on differential equations will take us. It will and it may be visiting some things you did last year in more detail, but it certainly will be taking you to new cases and new bits of analysis. So that's why we start with the forward Euler. It's almost the simplest, it has its uses, but it has its weaknesses, and we want to see how we can improve on that. And in the process, cement in these key concepts of accuracy and stability, these two people sitting on this swing, Mr. Accuracy and Mrs. Stable, or the other way around. To help us understand, numerical methods. So that's, as I say, I'm not trying to just throw methods at you, different methods. What I'm trying to get is cement understanding of how it works, because I think that'll stay with you a lot longer beyond this module than just a whole bunch of methods. Okay, so on that note, I'll stop. See you next time.